because the mass of the modulus, so the mass of the speed, is also finite, is non-zero. Okay, finite, constant, but how much is that? So how much is the correlation length? How much is the mass? Well, remember, the mass in general, and also then the mass for the speed, is basically the curvature of the potential, because it's the coefficient of the Gaussian part, of the quadratic part. So how much is the curvature of our speed controlling potential, right? V, this is V, this is our reference value V naught. So remember the Gaussian expansion, we just did that in the previous slide, was V going like 4 V naught square G VI minus V naught square. So you clearly see that the second derivative at V naught, apart from constant, which are really constant like V naught itself, scales like G. So that puny parameter that we never touched up to now, so the prefactor of the speed controlling potential, also regulates its second derivative at its minimum. So this means that the mass square of the speed is proportional to G. Okay, so from what we learned the other time about the mass square and the correlation length, so maybe I should stop my video, sorry, because I get a very big delay. Okay, there you go. Right, so from what we saw the other time about the relationship between correlation function, correlation length, and mass, so the speed correlation length was 1 over the mass, that is 1 over the square root of G. So then perhaps we do have some, margin of improvement of our theory. Because what we see is that when the G grows, the correlation length, when G decreases, the correlation length of the speed grows. So let's give a name to this G now. So G, we will call G the stiffness. It's really how stiff is the potential around its minimum, okay? So this is the axis of the modulus of V, the speed, this is V naught. So for large G, you have some very narrow potential, while for small G, you have some very shallow potential. So if we decrease G, we increase the correlation length. And remember, the whole problem we had that the correlation length in our data is larger than the correlation length in theory. So can we use G? Can we tune G to reproduce scale-free correlations? Well, at first it seems impossible. Why it seems impossible? Well, because we said the other time that psi scaling with L, a scale-free phenomenon, seems to require a bulk correlation length, which is infinite. But this then would require G, a stiffness, a speed control stiffness, which is 0. And so this would mean no control, no potential at all. So an unbounded speed. So this seems totally to make no sense at all, right? So it seems that this is impossible. However, as usual, we have to be very careful. So let's see this with more care. So imagine that you have a bulk, so an infinite size correlation length psi, which is truly infinite. So what happens in finite size? Well, what happens in finite size is that if you plot now the finite size correlation length as a function of L, the size of your system, yes, you will see a scaling behavior, a scale-free behavior. So psi growing with L. Up to when? Well, up to the maximum size of your data. So let's call this L max. So if you are at finite size, it means that you have data up to a certain finite size. Let's say the biggest flock you have in your data, right? Okay. So certainly, if the bulk correlation length is infinite, in finite size, you do get this, so you do get scale-free correlations. But now imagine that the bulk correlation length is not infinity, but is, I don't know, 100 meters. So you have tuned your parameters in your theory, whatever is the correlation length that we're measuring now, not only the speed, this is a general argument. So the bulk correlation length is 100 meters. So for example, you take a system close to criticality, but not exactly criticality, right? Okay. So what would you see in finite size? Well, so this is the L axis. This is now the finite size correlation length. So what you see is that actually you see that psi grows up to its bulk value. So this would be its bulk value of 100 meters, right? So this means that for flocks smaller than a certain size, you do see scale-free behavior, right? If the largest flock that you have in your data set is here, okay, then you see a scale-free behavior, but then you also see a saturated behavior. So a constant psi. So in this case, you would say that there is a violation of the scale-free behavior. Fine. So clearly, this is not a scale-free system, but it's important to know that for flocks which are small, in that regime, you would see a scaling correlation length. But so now you understand that if you take, so let's keep that there. If you take a bulk correlation length that is, I don't know, 1,000 meters. So this is bigger than any flock. You never see flocks as wide as 1,000 meters, okay? So this is still a finite correlation length. It's not an infinite correlation length, it's a finite one. So what do you observe when you go finite size? Well, so this is finite size, psi. Well, you observe just a scale-free behavior. Why? Because your maximum size, maximum observable size, is too small to detect the saturation. So if it could go on, you would see something like that, and then a saturation to the value 1,000 meters. But because real flocks are much smaller than that, well, they can be within 100 meters, 200 meters, but not 1,000 meters, then you only see scale-free. So in a way, you see that I've cheated you. When I said that a scale-free behavior implies an infinite correlation length, that is not true. What a scale-free behavior implies is that the bulk correlation length, in this case, the correlation length of the speed, must be much larger than the larger object, the larger system you have in your data set, L max. So this is the largest flock. If you have data up to 200 meters, which is more or less what we have, or perhaps 100 meters, well, we do not know whether the underlying theoretical correlation length is really bona fide infinite or not. We can only say, well, it's certainly much larger than 100 meters. So this is very handy for us now, because if now you remember that in this theory, Landau-Ginzburg or linear speed control, the speed correlation length goes like 1 over the square root of the stiffness. So we conclude that we do not need actually zero stiffness. We simply need a stiffness much smaller than 1 over L max squared. Well, be careful here. There are many other dimensional parameters to make the dimensions right. I don't care here. It's Friday night. I just want to give you the main idea. All the other parameters here do not matter at all. The important point is that if G, if the stiffness of the potential is small enough And small enough means much smaller than 1 over L max square, when this should be okay. Should be okay, meaning one should get scale-free speed correlations. And this is fine because G would be small, but finite. So there would still be control. It's not that there is no bounding potential. You still would have a confining force around the physiological value V naught, the physiological 12 meters per second of birds, right? But it would be very shallow, but still you would have control. So this seems to be a good idea to pursue. And before telling you whether or not it works, I would like to remember just one theoretical, well, it's not a problem for now, but let's say one theoretical each. Something which we are not entirely happy about. And the theoretical hitch is that there is no thermodynamic limit of this theory. Why? Well, clearly, because if L max goes to infinity, well, then you would require G equal to 0, which means no control. So this would be just an unbounded theory. So the modulus of your velocity is free to take any value, which is absolutely impossible. And this is not very nice on one hand. On the other hand, one can say, well, what the heck? Flux are always finite. So maybe I don't need to do the thermodynamic limit. Well, who cares? Yes, fine. It's a theory without a well-defined thermodynamic limit, but I'm doing biology here. I'm not going to have 10 to the 23 starlings in my flock. So I don't care. There is no L max goes to infinity limit. And if I'm bold, I can say something more. If I'm really bold, I can say, in fact, I can say that biology, evolution or whatever, biology has fixed G to some value. And because of that value, then you only find flux up to L max of order 1 over square root of G. So this would be really trusting our theory, saying, okay, G cannot be 0 because you need some control. Okay, so G will be some small number set by some biological constraints. I don't care. But now once you have a value of G, which is a biological parameter, then you can get any flock because for some reason you need scale-free correlations because the whole is more than the sum of its parts, whatever. Those are really precious stuff. So this puts a constraint on the maximum size you see of the flock. And in fact, you do see, well, not in our data, but I mean, anecdotally, I've been on the roof taking data for many years. There are very large flocks, but they're not infinitely large flocks, right? Even those very, very high in the sky, at some point, there is a kind of a maximum size, beyond which they just disband, they break apart, right? So this is a possibility. So this first problem here, perhaps is not much of a problem, but just keep it in your mind for later. So this theoretical itch. So now the question is, does this idea work? Well, yes, it works. So to check whether it works or not, let's go again to SPP simulations, okay, with now variable values of G, of the stiffness. Remember, the stiffness is just how shallow or not shallow is the potential around V naught. So if you do these simulations and you measure in the simulation the correlation of the speed, so first of all, let's put the biological data here, not the simulation. The data, we know that they have linear scaling, right? So the data have really a linear scaling of this correlation length with the size. So these, the big points are biological data. Okay, we can do simulation with various values of G. So let's take a large value of G. So if you take a large value of G, what you see is something like that. So there is a small, tiny interval where the situation is scale-free here, but then you quickly saturate to your bulk value of the correlation length. So this is what happens for large G, which was to be expected, right? Large G has small bulk correlation length, so you immediately saturate to the bulk correlation length. So remember that psi spinodal goes like 1 over square root of G in the bulk. Okay, so you take some smaller value of G, okay, then you get something like that. So let's say this is a medium G. And then if you take a really small value of G, you find something like that. So this is really a small G. And how small? Well, G much smaller than 1 over your L max squared, where L max would be this value here, the maximum scale of your flux. And so in this case, you get scale-free behavior. So yes, it works. There would be saturation eventually, but I can't see it because I only have flux up to a certain size. So what you'll be doing is that by decreasing the curvature of the potential around its minimum, around V naught, we are able to increase, to boost the correlations in such a way to get scale-free correlation in all the observable regions. So it works. All is good then? Well, not really. So it works, but there is a problem. And the problem doesn't come from the scale-free part. So the scale-free part is finally accounted for. So we have a theory which is able to create scale-free correlation also for the speed. So where are the problems from? Okay. So problems with linear control. There's actually one problem. So let's take a new experimental entry. The speed of the whole flock. Let's call this S. 1 over n sum over k of dk. So this is the speed of the group, right? So this is the speed of the whole guy. So how large are the fluctuation of this thing? So we do have an experimental probability distribution of this quantity because we have several flocks, well, not 1,000 flocks. We have about 20 flocks, something like that, right? So we have a very sketchy distribution, right? So, but apart from being very sketchy, the most important thing is that it is very boring indeed. So the average, it is about 12 meters per second, which is not surprisingly the typical speed of a single starling, okay? And you have fluctuations up to, I don't know, 14 meters per second and down to 10 meters per second. So you have some fluctuations, but everything is really very boring. So you have no long tails, no outliers, and this is absolutely intuitive from the biological point of view. I mean, these are real birds flying in air, so it's not that they can do whatever they want, right? So, and does this S, the speed of the flock, depends on something? Well, we don't find any dependence on anything. So S does not depend, for example, on the polarization phi. S does not depend on the size of the flock n. And finally, S is very close to the V naught, let's say, of single bird. So I would really like to emphasize that this is the most trivial piece of experimental information. Let's define trivial piece of experimental information. No journal would ever publish this. Even though it's the first time you actually measure the speed of group of real birds of 1,000, 3,000 birds, if you send this to any journal, say, hey, I've discovered that the average speed of the flocks is the same on the individual bird, they say, okay, thank you, but no thank you, right? So it seems that funny then that from this really humble piece of experimental evidence came a kind of a breakthrough for this theory. So let's now summarize all of our experimental evidence up to now. So number one, remember, phi is close to one, so you have large order. And how do you achieve that? Well, easy, low noise or low temperature, if you want. And we are able to do that. Second piece of experimental information, scale-free correlation of the speed. Okay, scale-free. Now I'm also able to achieve that, small stiffness. Okay, so this is okay. Third piece, the most humble piece of experimental evidence. S is moderate. Oh, you have very moderate fluctuations of the speed of the group. So you have, let's say, reasonable speed of the group. It doesn't even seem a piece of experimental evidence. Sorry, the fact that the correlation length of the velocity is scale-free, I don't even put that here because that is granted by the Goldstone theorem. We didn't have to do any work for that. You don't have to tune anything for that, okay? So everything seems to be okay, even perhaps this third point, but still, we should check. Is this okay? So the new theory, is it able to grant a moderate, a reasonable speed of the group? Well, let's see that. Okay, so you should take S, which is 1 over n sum over I of vi, and calculate the distribution of S in your theory. So this is not a piece of cake because, as we said, the theory is definitely not Gaussian, despite being called linear speed control, but under some approximations that I will spare you, you can do this calculation. What you have for this the distribution is the following: 1 over some normalizing factor, s squared exponential of minus n sides of the group times g over t is the temperature or strength of the noise, if you want, s minus v naught squared. As I said, I will not derive that, but consider the various species. This is not really surprising because remember, the potential itself is G times VI minus V naught square, right? So this clearly is what goes here in the exponential. Then what is the S square in front of everything? So this S square here. Well, that is just the Jacobian. That S square is just S to the D minus 1 in D equal 3. Why? Because when you do this integral, you have to marginalize over the orientation. So you will have some integral in d di that you will write with some angular part, and then you will have the integral over the modulus times vi to the d minus 1. So this d minus 1 is what you actually find here as this S squared. So this is, sorry, this is in d equal to. Okay, so this is a funny distribution, and it's particularly funny for the role of this factor here, n times g, size of the system times stiffness of the potential. So to understand what is going on, you can compute exactly really, you can also evaluate the mean, of course, the average and everything, but it's very easy to compute exactly the maximum of that distribution. So let's call this the typical speed of the group. So if you maximize P, right, what you get is 1/2 V naught times 1 plus the square root of 1 plus 4t over n g V naught squared. This is an important result. And you may start seeing what is going wrong with this. So this, again, remember, is the typical speed of a flock. Its size n and stiffness g. So first, the good news. Well, the good news is that for n going to infinity, well, we know we are not supposed to do that, but let's say for very, very large n, what you get is that the typical speed of the flock is just V naught. And this is okay, is what we see. But you have a big problem for finite, actually small n, well, then you have troubles. Because what happens is that S grows when n decreases. What is worse is that because you have this combination n times g, right? And because g is small, and you have n times g inside that expression, it means that even largish flocks, that is flocks with n which is not very, very small, will have an reasonably large speed. And this is a problem because we saw that the group speed is totally boring. So for small n, the flock speed becomes unreasonably large. And the reason of that clearly is because we have to get a small g in order to grant the scale-free correlations. And mind, I'm not just saying that the fluctuations of the speed is becoming large. I'm saying that the mean, the maximum of the distribution, so also its mean, everything is blowing up for small n and small g. So one can say, well, then increase g, increase the stiffness. But we can't, because we know that if we increase the stiffness, we lose the scale-free behavior. So it seems that we are trapped. So before really seeing whether or not we are trapped, but we will be trapped, let's see why this happens. So why the speed blows up? Well, the distribution of the speed of the flock was 1 over z, I write it again, s squared exponential of minus ng t s minus v naught squared. So you see, the problem, well, there are many problems, but certainly a problem is this factor s squared in front of everything. Without that factor, you would increase the fluctuations by decreasing the stiffness, but you wouldn't increase the mean. But that flux, this factor here is really what boosts the speed of the flock. So where that factor is formed, well, remember that is an SD minus 1 ds, which was coming from the VD minus 1 dV. So it's just a Jacobian. In the change of variable between going from vectorial V to the polar representation, the speed. So this is just a very trivial entropic contribution. It's an entropic factor. Why entropic? It's telling just the fact that you have many more ways to realize large vectors, large velocity vectors, than to realize small velocity vectors. So this is why the velocity is blown up. And by the way, this is the most trivial factor on Earth. This is there exactly the same also in the maximum distribution of the speed in a gas. So it's just telling you that because of this very trivial factor here, well, you have an entropic drive to blow up the velocities, and due to the fact that you have more vector with large velocity than vector with small velocities. But normally you would have that the exponential depresses that. However, here the exponential is not working because you have a small g. And so you have a problem. Is this problem real? Yes, it is very real. So let's go back to our very good, very useful SPP simulations. Okay, so we saw that we were able, so let's plot here speed correlation versus size. Okay, so this is the data that we want to reproduce. And here now let's plot the speed of the group, the speed of the flock versus number of birds in the flock. So what I told you before is that there is no dependence whatsoever, just very small fluctuations. So we see before what happens on the left. So if you have a very small g, you do see scale-free behavior. If you have an intermediate g, you see scale-free behavior only up to a point. And if you have a very large g, you find very poor scale-free behavior, right? So the blue is large g, the purple is medium g, and the red is small g. Where small means, remember, much smaller than 1 over L max squared. So what happens if you do the same simulation here? Well, if you have a large enough g, so the blue case, there is no problem. You have a speed of the flux which is totally under control. And now, if you start decreasing the stiffness, so if you start making the potential more shallow, what happens is something like that. And if you take G small enough to have the scale-free correlation, okay, you get something like that. So you would have that your smaller flock, smallest flock, is supposed to go at, I don't know, 100 meters per second, which is absurd. So, and let me put here the different cases for the potential. Remember this, we're just talking about the stiffness of the speed controlling potential. So this is B naught. So red means very shallow. Purple is a little bit stiffer, and blue is very stiff. So this is what I would call a blanket too short dilemma. You either get scale-free correlations or you get a reasonable group speed. You cannot get both. So if you have scale-free correlation, okay. So if you are in the red case, fine, you observe specific correlations, but then you have an absurdly large speed of small, well, not only small and medium flocks. If you want to get a reasonable speed of the flock at all your observed sizes, fine, you can do that, but then you lose the scale-free behavior. Okay, so in conclusion, linear speed control plus small g does not work. Small stiffness does not work. Because after all, the data is always right. To be honest with you, the people who first realized that with a small g you could fit data, it was actually ourselves, so my group. So we were the one only seeing this side of the story first in 2013, and we were very happy. We didn't see at all this side of the story at the time. And you know what? Because we didn't have enough data, we only had large flocks. It's not that it was difficult to get data on small flocks. It was simply that because we are statistical physicists, we focused on large systems. We thought that everything interesting was only for large N. So we didn't have the data to see this left absurd part. So then we went out on the roof again a few months ago, actually. We've got some new data here. And we saw that, of course, there was no dependence on N. And then we got the idea and we said, okay, so this cannot work. So sometimes we get it wrong. So the theory doesn't work. And let me say that the theory anyway had something weird because remember, we are doing lambda phi 4. So it's a good old Mexican. And G, remember, is the factor in front of the potential. So decreasing G actually meant to decrease the whole potential. So to make it very, very shallow. So not so shallow how to make it disappear, but clearly the problem was that in order to have V second small, we needed G small, but this made the whole V small, the whole potential small. So it was kind of an overshooting. In order to have a small curvature, in order to have a small mass, we were killing the whole potential. So then the question is, can we conjure up a speed control potential whose curvature along the modulus is small, but in which the whole potential is not small, it remains stiff, it remains strongly diverging for large values of the speed. So to answer this, let's go back to our original form of the Hamiltonian and in particular of the potential. So sum over I and j, well, we certainly will remember this form by the end of my course. At least one thing will be informed. Sum over I of V of VI squared. So what we know of this V potential of VI squared? So we said that the most general and simple form we can imagine is the following. VI, I explicitly write VI scalar VI because I want to emphasize that this is a function of the vector, right? Minus V naught squared to the power P. This is very simple and it's the minimal potential because it is rotational invariant. And then for P even, it has a minimum. It has a minimum at V naught, which is what we want. Okay, so we saw that P equal to is not working. So the standard Landau-Ginzburg model or ON, so this is Landau-Ginzburg, also called in the vectorial case ON model, also called linear quotes speed control. Okay then, so instead of trying now to think and find some other reasonable way to constrain the speed of the birds, let's just try the next case, the simplest case beyond the one which doesn't work. P equal 4. Will this work? So this is the simplest case beyond linear control. So let's try it. Let's see what happens in this case. What is the shape of this potential? So this potential V will be G times VI squared minus V naught squared to the 4th. So what is the difference with the P equal 2 case? Well, there is a remarkable difference. So let's draw again the potential in the P equal 2 and let's compare it with the P equal 4 case. So let's first see the speed view, right? So just cutting in the speed direction. So this is what happens for P equal 2. So you have a minimum here at V naught, and in order to tune the curvature of this minimum, you really have to make the whole potential very shallow. Now the P equal 4 has an easy but very handy property. It also has a minimum at by V naught, but the second derivative is always 0. It's flat, independently of the value of G. So this is the P equal 4K. So probably the drawing is not clear enough. So let me write this down. So here in the P equal 2 case, to decrease the second derivative at V naught, you must decrease G, which is not only the stiffness, it's the amplitude of the whole potential. And this was the problem, because by decreasing G, I really go down to a potential which is not bounding at all. And this is the cause of unreasonable group speed. On the other hand, for P equal 4, what you have is that V second at V naught is always 0, irrespective of the value of the amplitude. If you don't believe it, you can do the algebra. It's very simple. So because of this larger power here, this is something that has 0 curvature at its minimum, no matter the value of the amplitude. Okay, because it's non-Gaussian in that direction. So because I always give you the rotationally invariant view, I will try to draw that also the rotationally invariant view. So let me do the Mexican hat view. So if P equal 2 is something like that, the usual lambda phi 4 potential, right? So here are the velocities. And as we said many times, you have a line of minima. And the curvature around this point, so this curvature here is non-zero. In order to make it 0, you have to depress the whole potential. Now, how is this other potential? Well, I don't really know how to draw it, but it would be, well, it is something like that. So instead of having just a line, a flat line of minima, you have a sort of a strip, a flat strip of minima turn around. Well, it's just a second derivative, which is 0. It's not. It's still an analytic function, okay? So you have that. Here you have your line of minima, but around that line of minima, also the curvature in that direction is 0, right? Also the curvature in the longitudinal direction, good old longitudinal direction is 0. And this will be a game changer. So here the potential is flat. So V second is equal to 0 also in the modulus direction. No matter how large or small is the amplitude. So because of this extra 0 mode, 0 modes are also called marginal modes, okay? We call this the marginal potential, so marginal speed control. While this one on the left is, funnily enough, I repeat, but called linear speed control. But at the level of the force, it makes sense, okay? So linear and marginal speed control. Okay, so remember, there are two again, crucial features of this new potential. So feature number one, the second derivative is zero in the direction of the modulus irrespective of g, of the amplitude, okay? And feature number two, because you don't need a small amplitude, the potential is still very much going to infinity at its border, so bounding the speed in a much more effective way. So the two fundamental features of the marginal potential are, number one, that v second along the speed at v naught is equal to zero irrespective of the amplitude g. And so this means that the mass of the speed, the bare mass at least, is zero. And so there is a chance of having scale-free correlations, but we have to check that. But the second point is that because we do not need a small g, because the curvature is already zero, v goes to infinity when vi goes to infinity very sharply. We are not depressing the whole potential. So perhaps this will give us moderate group speed. Okay, we must check 1 and 2 theoretically. So first, let's go to point number 1. So point number 1 is a bit tricky because remember, the curvature of the potential is the bare mass. And we know that fluctuations, interactions, and other things can change the bare mass. So it's not as simple as that. We cannot directly read the mass and the correlation length from the bare potential. So let's analyze this more carefully. So point number 1, at the theoretical level, okay, does the marginal potential grant scale-free correlations? Well, scale-free correlation of the speed, remember, I mean, one of the velocity we have then thanks to Goldstone, and Goldstone is not changed at all by this potential because it's still a symmetric potential, we're still breaking the symmetry, so all the Goldstone part remains the same. So at the bare level, we would say yes, because here we already said that, but the second derivative of v naught is zero. So this implies that the bare mass of the speed, so of the modulus, is zero. So, but this is a bare result. So this would be okay. This bare result would be okay if the temperature was zero. So if you have no noise, right? If you have no noise, you have no fluctuations, so entropy doesn't matter at all. And so in the free energy, and remember the free energy is always a competition between the energy and entropy, and that competition is tuned by the temperature T. But if you are at T equal to zero, the free energy simply reduces to the energy. And we know that our energy has got, well, let's say the imitation part, and let me write it again, plus the speed control. So at T equal to zero, minimizing the free energy, which is actually what we have to do to find the state of the system, is the same as minimizing the energy, right? So minimizing the energy requires having all the V equal, right? So perfect imitation, of course, plus you need to minimize V. And to minimize V, you just get the 0 second derivative at its minimum, okay? And so you get scale-free correlations. So these at T equal to 0. But of course, at T equal to 0 is a very pathological case. Because, okay, the range of the correlations would be infinite. But if you don't have temperature, you don't have fluctuations. But remember, the correlation that we're computing is the correlation of the fluctuations. So you would have a very pathological correlation function, which has infinite range and zero amplitude, which is not something that we really want. But this is telling us that this is actually perfectly scale-free at zero temperature. And so you can ask, what happens if we put then some temperature in the system? So this is a calculation that you can do at mean field and also that we've done with the RG, but let's see at mean field what happens. So mean field level, well, ask Julie what mean field level is if you don't know what mean field level is. So at mean field level, you can calculate exactly, well, exactly, it's a mean field level, the Gibbs free energy. So, and what do you find if you compute the Gibbs free energy? So let's plot now the Gibbs free energy as a function of the modulus of di, so the speed. So this is Gibbs. So first of all, at t exactly 0, well, unsurprisingly, you get the same thing as the bare potential, which is flat. So this is not, but this is exactly what happens at t equal to 0. Again, it's unsurprising. At 0 temperature, free energy and energy are the same thing. Now, if you start raising the temperature, what you see is that you do create some small curvature. And the larger the temperature, the larger is the curvature of the free energy. So at large t, you get a v second, which is different from 0. At t equal to 0, you have a v second, which is equal to 0. And if t is small but not 0, so at t larger but still close to 0, you get a v second, which is small. Different from 0, but small. So what happens, and this is an interesting mechanism per se, forget about bursts, but what happens that entropy provides a non-zero second derivative of the Gibbs free energy. So entropy provides a non-zero renormalized mass. So entropy produces a non-zero renormalized mass, which in turns gives then a finite correlation length of the speed. So this, if you do the calculation in field, you can quantify this, and what you find is that psi of the speed goes like 1 over t 1 half at mean field. By the way, for those of you who already know about critical phenomena, this 1 half is the good old exponent nu, mean field exponent nu of critical phenomena. Normally is 1 over t minus tc to 1 half. But here, what we have is a 0 temperature critical point. So Tc is 0. So we have a divergence of the speed correlation at 0 temperature. That unsurprisingly, the mean field critical exponent is 1 half, because it is always 1 half. So we see that this theory has a very convenient 0 temperature critical point. Critical point. Very convenient. So first of all, 0 temperature critical points are not unheard of, while in quite different contexts, but forget about that. So why very convenient? Well, because, by decreasing the noise now, by decreasing the temperature, so by going to the left in this axis of the noise, of the temperature, you bring home 2 out of 3 experimental results about flux. So by decreasing the temperature, so by T going down, you get 1, order increases, phi goes up. And this is good because we know that flocks are very polarized systems. So we already wanted to decrease the noise in the theory in order to get a polarization of about 0.95, which is a really large polarization. But two, now you get home something else, correlation. Well, speed, correlation increases. So psi speed also goes up. And this is actually very unusual in standard critical phenomena. You know, normally the deeper you go in the order phase, the smaller is the connected correlation. But this is different. So before going back to birds and checking this, let me show you what is the scenario of the system. So let's put here the temperature, the strength of the noise. So first of all, this marginal potential has a very normal critical phenomenon at the finite temperature Tc. Because at large temperature, the marginal potential, the marginal free energy becomes just the same as the normal ON model. So the fluctuations erase the marginal feature at large temperature. So everything around the classical, the normal transition critical temperature is the same. And so what happens in this kind of systems? So you have a divergence of the correlation length coming from above, right? So psi is going to infinity. And because we are above the critical temperature, so above the breaking of the symmetry, we cannot distinguish between modulus and direction of the other parameter. It's just the global correlation length. Okay, so psi diverges when T goes to Tc from above. Okay, and this, the black line is the standard ON or Landau-Ginzburg. The high temperature phase of this new model, of this new theory, is exactly the same, no differences. Now, what about the low temperature? Well, low temperature, symmetry broken phase, you have the Goldstone phenomenon. So I cannot plot an infinite correlation length, but let's say that this very high line here means that the correlation length of the velocity fluctuation is infinite, and this is due to Goldstone. It's the Goldstone phenomenon. But you have exactly the same thing for this new theory. The correlation length of the velocity fluctuation, which are dominated by the orientation fluctuation, is infinite in all that in the low temperature case. But now, the correlation length of the speed fluctuations, as we know, well, it goes very quickly to a constant. It doesn't diverge at all. So C of the speed goes to a constant in the normal Landau-Ginzburg model. In this case, however, so this is marginal, red is marginal. So I know I'm cheating because you don't have colors, but well, apart that you should have colors, right? But I don't mind anyway. So in the marginal case, what you have is that the speed correlation length in the low temperature phase grows up again when you approach the zero temperature critical point. So by going down in temperature, by going at low noise, you also get large speed correlation, which is exactly what we want. Now remember, there was a third experimental trait that really betrayed us in the case of the normal ON theory, and was the one of moderate speed fluctuations, moderate speed value for the group. So how about that? So do we get, so this was the point number 2 in our classification before. So how about group speed in the marginal case? Okay, so we have to do a calculation. Well, I will not do it here. So remember, the group speed is 1 over n sum over I of vi. If you compute the distribution of the speed in the marginal case, you get a very similar expression, but with some important difference. You still have the s squared Jacobian in front, you have an exponential, you still have the ng here over t, but here, unsurprisingly, the power changes. It's no longer 2, it's 4. So it seems that you have only a very minor change. That is, you have just changed this power here. However, now you have to notice that G does not need to be small to get scale-free correlations, right? T, the temperature needs to be small, but the temperature is here at the denominator. So it's fantastic because by going down in temperature, we are depressing even more the crazy fluctuation of the speed group. Moreover, the power 4 in the exponential is very effective in depressing large speeds. And if you compute the typical speed in this case, well, so if you maximize that, it's no longer a quadratic expression, but if you do that, what you get is the following. You get V naught for large n. Large, what it means? Much larger than T over G. And then you got something else, V naught times T over N G to 1/8, or N much smaller than T over G. So this is fine for large flocks, but this also is fine because you see, you have very moderate increase. Moreover, the most important thing is the following. You start increasing your speed when n is much smaller than t over g. But now g has no reason to be small. It's a number of order 1. On the other hand, the temperature is small because we want strong correlation. So you don't see that increase. So it seems okay. But to check whether or not it's okay, the last final judge is always doing a simulation of self-propelled particles out of equilibrium, non-fixed network, the real deal. So let's do that. And let's compare, while we do that, let's compare also with the previous, the linear speed control case compared to the marginal case. Okay, so let's make some nice plot here. So I want to show 4 plots. So the upline here is linear speed control. So to the left, we have again the speed correlation as a function of L, data show a very linear increase, okay? On the right, we have group speed S as a function of N. Data show no structure at all. So what we saw in the standard case was the following. If you use a large stiffness, you screw up totally the scale-free thing, but you get a good non-crazy speed of the group. Intermediate, you half screw up the scale-free thing, and you half screw up the moderate speed thing. Very small stiffness, you have an excellent scale-free behavior, but you screw up big time the moderate speed. So this is what we had before. So the blue, so this is, sorry, this is large G. So the blue here is large G, large speed. and the red is small g. Right, so the red is fine on this side, but is screwed up on this other side. The blue is fine on the right, but is screwed up on the left. Okay, what about marginal speed control? So same plots, L, speed, data, group speed S, and data. Well, here, fortunately, we can just take one value of G and one value of the temperature, and you get scale-free behavior, totally moderate group speed at the same value of G. And G doesn't need to do anything. G of order 1 and T. And T must be small. But it must be small also to bring home large polarization, large order. So really, the marginal theory seems to work. It's explained in a well way. It reproduces in a reasonable way all experimental results simply by going at low temperature. So let me summarize them here because I don't want to change this slide. So order phi equal to 1, it's fine. You simply go at low temperature. Correlation C of the speed goes like L is fine. Even this, you get it by just going at low temperature. Finally, reasonable group speed. That is also fine. You basically have to do nothing to get that because you have a potential, which remember was a v squared to the fourth. So you have a power 8 to cut all your fluctuations. So you are fine on that side. It's absolutely, they're absolutely thin. Okay, I have another 10 minutes to tell you now an important part, which is the biological significance of this. So I will have to be quick, but let me give you a flavor of the biological significance. So it will be mostly word, at least for me. You have to write everything. So we arrived at this potential by simply adding one power, well, two powers actually, to our original potential. So we tried that, didn't work. Okay, so we said, let's try the simplest thing, the next simplest thing, which was this. We were guided by the experimental result. So we saw that the power 2 was not working, was not reproducing the experimental result, but we did not go and ask to a biologist or to an ornithologist, even better, what is the most biologically compelling way a bird would control its velocity. So after I found this and everything I told you today, so after I found all these results, I did ask to an ornithologist, right? Because I wanted to understand, I wanted to have some comfort at the biological level because we are doing biology after all, and biology rules. I mean, physics is nice, but at the end, the biological evidence is always most important, the most important thing. So I asked an ornithologist, and not any ornithologist. I asked to a guy whose name is Frank Hefner. You should check him out. He's now retired. He was at the University of Rhode Island, and he was one of the very first that in the 70s, as in the 70s, there were chemical cameras and film, no digital machinery. In the 70s, it really obtained the first 3D data on flocks of pigeons. And they had to do the tracking by hands. So that is an outstanding paper by Frank Hefner, and it was by Pomeroy and Hefner. So he's a great guy. He's a great guy. He's a great scientist. He doesn't know anything about physics, and I normally run all our arguments and results to him because he really doesn't care at all about ghost and field theory. I mean, he doesn't care. He only cares about birds, and he has got a lot of intuition about birds. So, what did I ask Frank? So I asked him about the confining force. Remember, biologists prefer to think in terms of forces, either real forces or social forces or effective forces rather than potential like physics. So what I did was to show to him the speed confining force in the two cases. So I showed him something like that. So on this axis here, we have the confining force. On this axis, we have the individual speed. Down here, there is V naught. So the two models are simple enough when you watch this. The linear control is actually a linear force. Now, what is the marginal control? So marginal, well, remember, there was just two extra powers, right? So if you compute the force, what you have is that you have a very non-linear force. So something which is very, very weak around zero, and then it grows very, very quickly. Okay, so these are the two kind of speed restoring force. And I asked him, Frank, what is your opinion about the most reasonable speed control force for a bird? Well, and he immediately replied, the red one, 100%. So once you know some biology, Frank does, this answer is actually quite intuitive and is very nice because the reason is the following. You can classify speed fluctuation into two very broad classes. Small speed fluctuations, okay? So this is not a small. So small speed fluctuations and large speed fluctuations. I know this is very qualitative, but stay with me. So marginal control is equivalent to say what? That small fluctuations, speed fluctuations, are free. You see, you don't pay anything there. It's the flat part of the potential. On the other hand, large speed fluctuations are fiercely suppressive. Fiercely is a word that Frank's always uses. So is why this makes sense at the biological level. So the marginal control potential is, at the end of the day, a very simple rule. It's telling you, small fluctuations, yeah, do what you want. Large fluctuation, no, no way. Linear control, on the other hand, suppresses at the same rate small and large fluctuations. So then why the marginal does make more biological sense? Well, there are two basically mechanisms responsible of suppressing speed fluctuations. So there are two broad reasons why not to have speed fluctuation. The first mechanism is energy expenditure. Well, they cost energy. Changing your speed costs energy, right? But the second reason is biomechanical constraints. Biomechanical constraint is something different. It's something to tell you that no matter how energy you put in the machine, so no matter how powerful is the machine cannot go at some speed. So no matter the energy you put, you cannot run at 100 kilometers per hour. So there are biomechanical and constraints which are related to the physics of flying, aerodynamics, anatomy, physiology. So really hard constraint you cannot overcome. So do they impact, so these two constraints, do they impact equally on speed fluctuations? Well, the answer is no, because small fluctuations could be depressed by energy, but they're not depressed by biomechanics. Because there is no reason why a bird cannot fly at 13 meters per second. It's just a matter of putting more energy or braking and so on, but there are no biomechanical constraints. On the other hand, large speed fluctuations, well, they may be depressed by energy as well, but certainly and most importantly, they are strongly depressed by biomechanics. Strongly depressed by biomechanics. There is a cut-off speed, more or less. By the way, note, both at high speed and at low speed, I mean, they cannot stall, right, like planes. So the important point now we should understand is, okay, so for small fluctuation, biomechanics doesn't depress them, so we can cancel it from here. So how relevant is the energy constraint on small fluctuation? Well, in this, Frank Hapner has always been very clear in the all 40 years of his investigation about starling flocks and bird flocks in general. For flocking birds like starlings, energy expenditure seems not to be a concern. So I'm not talking about migrating birds here. Remember, this is a symmetric case. So this is now the time I tell you a little bit about this bird. These are flocks which form at sunset over the rooster. And what they do is that they spend half an hour at sunset by swirling in the sky for apparently no reason. Well, they certainly have a reason, but we don't know the reason. But what is certain is that they are not eating, they're not mating, they're not defending themselves because they could stay much safer on the trees, but they do that. And while they do that, their energy expenditure is outrageous. They have a metabolic rate, they are small birds, they have a metabolic rate which is really outrageous. They don't care, they do that anyway. So this is why Frank would say, and I would agree, that probably also the depression due to energy of small fluctuation is simply not there. So that at the end of the day, you know, what we conclude on the basis of some biological common sense is that small speed fluctuations, they are not depressed by energy, but by energy considerations, and certainly not depressed by biomechanics. On the other hand, large speed fluctuations probably also they are not, or we don't know, maybe it doesn't matter, they are depressed because they're large, maybe they're depressed by energy, but certainly they are strongly depressed by biomechanics. Well, what is the picture of these 6 sentences? Well, if you have to translate these things into a force, confining your speed around some value V naught, well, then you do exactly that. Perhaps not exactly the power that we put there, but it doesn't matter. And it also doesn't matter in the physics. The important point is to have a strongly non-linear confining force, which leaves you free to do this, but says, no, you cannot do that. And this is just a marginal potential, which gives you scale-free correlation, strong order, and reasonable speed of degree. So biologically, we're also okay. Okay, so I will come back to you live to give you my final remarks. We are almost there. Well, I'm out of time. So the message is, if you want to study and understand collective biological systems, so the collective part of biology, I strongly urge you to study statistical physics and field theory. But the classic ones, the old stuff, Goldstone theorem, Mermin-Wagner, Higgs mechanism, when we studied the spontaneous breaking of the continuous symmetry, we were one step away from the Mermin-Wagner theorem, which is an incredibly important result, even for biology, and 3 steps away from the Higgs mechanism, which, okay, perhaps is not relevant for biology, but you never know. And it's the, the Higgs mechanism. So it's very fundamental in classic physics, the renormalization group, all that thing. So I hope I show you that this is really stuff that you really need to learn to understand things, even at the biological level. And sometimes you get lucky and you get a result just from physics that is also relevant for biology. Okay, thank you.
Thank you.
All right, so this is the last lecture by Andrea. So other questions on this lecture or more general ones? So come here.
Hi. You said earlier that maybe the maximal size of the flux you observed, maybe due to some parameter of the interaction. But are they simulation results where you actually measured what was maximal flocking size possible? And did you observe a difference?
Well, I've said that in the context of a theory, which I think now is no longer the right theory. So I said that in the context of the linear control theory. In the linear control theory, yes, if there were a biological value of G, then you would have a maximum value of L. That maximum value, yes, if you do the simulation, you get exactly that. That maximum value of L scales like 1 over the square root of G. However, I don't think that that now is the correct theory. In the correct theory, you have a different potential, the marginal one, where you do not need to tune G. So in that case, what controls your maximum size, if you want, would be the amount of noise.
Yeah.
Okay. Well, in that case, yes, you can link the two, but the problem is that flux are so ordered, so there is no conflict in this new theory. There is no conflict between going at low temperature, getting large order and large correlations. So you don't get any constraint of that kind. So I could imagine that in order, so the idea of this new potential would be, in order to form very large flux, still having scale-free correlations, you need to have a very good alignment. But the alignment of these guys is just already so amazingly large that it's hard to believe that it can become any larger. So it's really, in a way, a comfortable theory. You don't have to tune anything much to get all the 3 results.
So then, for actual birds, the limit in the size of the flux is not due to the amount of noise. It's due to the number of birds or something.
Okay. If there is a limit in the value of n, I would say that is due to something else, but it's an entirely different part, and that something else is the propagation of information. Okay. So everything that I did in my lecture was, let's say, statics. However, you can start studying the dynamics and how signal propagates across a flock. If you do that, you see that you have a competition between dissipation and propagation. And what you see is that very large flux. So if you go towards the thermodynamic limit, so toward the hydrodynamic limit, so K going to 0, you seem inevitably to enter in the overdamped phase of information propagation. And then what would happen in that case is that if you start a turn on the lower side of the flock, it propagates for some distance and then it dissipates. So the guys down here would turn to the left, but the information wouldn't arrive to the guys on the up, and then you break up the flock. But that is an entirely different part of the theory, which is the dynamical part.
Okay.
That could, I think that is what sets the largest size of the flocks.
Okay, thank you.
Other questions?
But maybe connected to that, the correlation is very short.
Just to follow up. I'm allowed to make questions. No, I had a similar question as the student before, so it's and now it's very small. It's just whether, so there is a dynamical correlation that then comes up. So that will be smaller than the static one. That's my very short.
What do you mean by smaller? The dynamical correlation defines a correlation time, a relaxation time. The static one defines a correlation length.
No, sorry, you said that there is propagation until a certain distance.
Yes. Okay.
And then
so propagation is dynamical propagation is connected to the correlation, is not the same as the correlation function. Okay. So in order to see the propagation of information, you have to have some perturbation and you see how that propagates. But the two things are connected because they're connected to the dispersion relation.
Mm-hmm.
So the dispersion relation has a static part, which is the same static part that you see in our case, plus some omega part. And the omega part in the original theory, so in the Wiczek theory, is overdamped. So it would be an I omega. So the dispersion relation would be I omega equal K squared, which is an overdamped one. Now we developed a theory where you have a second order dynamics, in which the dispersion relation becomes omega squared equal C squared K squared, where you do have propagation. However, you always have dissipation. So you have a terms I omega times eta, some dissipation in the dispersion relation. So in that case, you have a finite, let's say, propagation distance of the signal. And then that is what sets the maximum size of the flock.
And that would be smaller than the relation length from the static theory in principle, because you said that that would be much larger.
Well, yes, but there is something worse, because in that case, what is really matters is the dynamical correlation and the propagation of the orientations. Now, for the orientation, the static part is trivial, it's just Goldstone. But the dynamical part is not trivial. So in that case, the speed is actually your secondary concern, because what is really crucial for the birds is to propagate the directional information, basically to turn away from a perturbation, to turn away from the falcon, to turn away from something, okay? So in that case, yes, of course it's smaller, because the static one is always infinite. I mean, it's always Goldstone, so it's basically not there. While the propagation length of the orientational signal is finite because you have dissipation.
Okay.
Hi.
Hello. Hey. Wow.
So I have a question about the difference between zero temperature and finite temperature. So you show the critical exponents in mean field for the correlation length of the speed. So I suppose that you can go behind mean field and find to compute finite size correction to this. So what will be what will be?
We are writing that up right now with the students. So with the RG of this theory.
Okay.
And it's very funny, because what you see is that it is infrared free. So you get at one loop, you get exactly the same exponents as the free theory, so as mean field.
Okay,
So
one up.
they seems to be protected by the zero temperature critical point. It's kind of convoluted, but you can do that at one loop at least. And it seems that yeah, basically the fixed point has got some extra T values. So at the zero temperature fixed point, the one loop correction to the critical exponent are driven to zero. And so we believe that the mean field exponents are actually the correct exponent. And when we did simulations in finite dimension, indeed we found results which were perfectly compatible with mean field. So we said, okay, the corrections are small, but remember the corrections to the correlation is eta, and eta is normally 2 loops. But this theory actually has a triple vertex, has a cubic vertex. So cubic vertices very easily create one loop corrections.
Enough to,
So I was confused because I thought, well, it's strange because if you have one loop correction, you should have large the correction to the critical exponents. Why in the simulation we find those? But if you do the calculation, you find that the theory is infrared free.
okay.
This is a spoiler. It's not even on the internet, so don't say anybody.
Okay. Thanks.
I was going public. Okay, yes.
Hello, related to this last discussion, I would also have a question. Like you say that when you try to do the renormalization procedure, these exponents seem to be protected. And I wonder if you have in mind, like, is there any general mechanism to protect these mean field exponents when you go to finite dimension, or it is something very particular from this theory?
I think it is something very particular to this theory, and in particular to the fact that you have a zero temperature critical point. So no, I wouldn't say at all that you have a general mechanism for protecting critical exponent to be equal to their mean field case. So it's certainly due to the zero temperature critical point, and possibly to this particular zero temperature critical point. I mean, when you do the calculation, the algebra is kind of intricate, so it's hard to understand how the result comes out, but it comes out. But certainly there are some amplitudes proportional to t to some powers, which depress all the renormalization group corrections. So I'm finding this general mechanism.
Finding this in temperatures that are different from zero would be very, very strange, right?
Absolutely.
Okay.
Absolutely. Totally.
Thank you.
Strange. No problem.
Thank you very much.
Other questions? Okay. Just a curiosity. So you cite many different things of classical, let's say, statistical physics and field theory. Can we think at topological defects also in collective biological motion, or no, there are no examples?
Yeah, well, absolutely. Not in what I do. So what I do is normally called dry active matter. So there is no strong interaction and feedback with the medium, but or everything wet active matter. So cells and bacteria and things like that, yes, you do have a big role of topological defects. Cristina Marchetti, but also Julien Tailleur, they are big on those kind of things. So yes, all sort of classical physical results are incredibly useful, and so it's full of kind of hanging fruit, which are very easy to catch by using a very old physics. So this is why I'm encouraging. So and it will not stay like that forever. So this is why I'm encouraging students really to study field theory, because I mean, fruits is not going to stay there forever at hanging level, catching.
All right. Okay. So well, thank you very much. So well for the lectures, for giving them the lecture despite all the problems, and sorry for the technical problems at the beginning. Okay. Of course, we will miss you, and well, you will come to Rohu next time.
Okay.
So thank you very much.
Goodbye, guys. Good luck. Bye. Thank you.